In this module, we will talk about media sterilization in batch mode. So when we talk about, when we say that batch mode, how we design the batch sterilization. So let's see that the batch sterilization process is less successful, as we have seen in our previous module, that the most suitable is the continuous mode, because this batch mode leads toward the destruction of the nutrients more than that the continuous one. So the objective in the designing of batch process is still to achieve the required probability of obtaining the sterility with minimum loss of the nutrient quality. So the highest temperature at which the feasible for the batch sterilization is 121 degrees Celsius. So the procedure should be designed such that the exposure of the medium to this temperature is kept minimum. So the time of this temperature in batch mode should be as minimum as possible. So this achieved by taking into account the contribution made to the sterilization by heating and the cooling period in batch treatment. Because when we say the batch mode, so that required 3 steps. So that these steps discussed and reported in detail by D. Indorfer and Humphrey in 1959, in which they present a method to assess the contribution made by heating and cooling periods. So the following information must be available for designing the batch sterilization process. Number 1, a profile of the increase and the decrease in the temperature of the fermentation medium during heating and cooling period of the sterilization cycle should be noted. The second, the number of microorganisms originally present in the medium. The total number of cells, viable cells present in the object, especially in the medium, that require their death. And the third one is the thermal death characteristics of the design organism. So that is basically explained that mostly designed, if we talk about the Bacillus stereothermophilus or any alternative organism relevant to the particular fermentations. So these are the 3 information we should know before designing the batch sterilization. So knowing the original number of the organisms present in the fermenter, or we can say the risk of contamination considered acceptable, the required del factor may be calculated. You know that we have discussed the del factor in our previous module, and I told you at that time that we will discuss in detail in a later module. So if we say that the frequency of the adopted risk of the contamination is 1 out of 1000, which indicate that NT should be equal to 10 raised to power minus 3 of the viable cells. So it is worth reinforcing at this stage that we are considering the total number of organisms present in the medium and not the concentration of the organism present in the medium. So if a specific case, if I take an example, if a specific case considered where the unsterile broth was shown to contain 10 raised to power 11 viable cells, then the del factor may be calculated. So the del factor is equal to ln into 10 raised to power 11 over n 10 raised to power minus 13, and then the answer will be 10 raised to power 14. So the answer will be, when we take the log of nature of 10 raised to power 14, then is 32.2. So this is the del factor when there will be viable cells at 10 raised to power 11. So if the del factor is required is 32.2, then at 121 T, the overall del factor and the contributing factors in the overall del factor is the heating, holding and cooling. So the one del factor that required to heat to raise the temperature up to 121 degrees Celsius, and then the holding time, and then is the cooling time. So knowing the temperature profile for the heating and the cooling of the broth, that is basically, it is possible to determine the contribution made to the overall del factor of the sterilization. So thus, knowing the del factor by heating and cooling, then it will be easily calculated for the required del factors. So as reported by the scientist in 1959, then the del factor contributing are the heating, holding time, and then cooling time.